everybody. Thank you all for joining us for this session. My name is Noah Herzenstein, and I'm leading product marketing here at PlaxidityX. And with me today, I will be co-presenting with me my colleague, Jonathan Lekov, product manager. And let's take a quick look at the topics that we would like to cover in this session. Really briefly, we're going to start with an introduction to the need, the importance, the criticality of doing vulnerability management in automotive software. Then we're going to talk about the two sides, the concept of shift left. So doing the vulnerability management while you are developing the product, while you are writing the code, and then kind of moving to the right side of the project timeline while we are kind of closer to the product being ready, and we have all the integration with our supply chain, making sure that we are covered on that side as well. And then I'm going to talk about, and this is really cool, integrating the vulnerability scanning process into your risk models. In other words, into your TARA, and we're actually going to see a demo of how this would look like in real life. And we'll circle back and talk a little bit more about regulation and how it all ties together. All right, so let's go ahead and get started with a quick introduction. I think everybody is aware of the importance of looking into vulnerabilities in our automotive products. And we're not talking, of course, about a theoretical issue. It's not that there could be vulnerability that could have some impact. We have more and more cases, and you see here some examples just from recent news articles about actual vulnerabilities that are being discovered in actual vehicles that are on the road. And if we looked at the vulnerabilities that were kind of in the news and that were discussed a few years back, those would usually be vulnerabilities that allow you to have access to the vehicle, but required you to physically be next to the vehicle. So in order to get into the vehicle network, in those kind of vulnerabilities, you need to have physical access. So for example, if you have access into the vehicle, there is the diagnostics port, or if you don't have access, if you're outside the vehicle, and there were some in the last couple of years, some really interesting examples of how you can sometimes even pull the bumper and get access to the CAN bus by accessing the wire that connects to the headlights, and by that, unlocking the vehicle and disabling the immobilizer and stealing the vehicle in 30 seconds or less. But those type of vulnerabilities, again, since they require physical proximity to the vehicle, they're not really scalable. So you can do it to one vehicle or to a handful of vehicles. It's more difficult to do it to 1,000 vehicles, to 1,000,000 vehicles. But in recent years, you see some examples, some references, even here in those titles on the screen. In recent years, as vehicles are becoming more and more connected, we are talking and we are seeing vulnerabilities that allow you to access the vehicle from remote. So there are APIs, sometimes the APIs that are used by the mobile app. The app that you use as a vehicle owner to access the vehicle, or through all kinds of services that are being done in the back end from the cloud. But here we're talking about exploiting vulnerabilities that allow you to access the vehicle from remote. And this is really a whole new ballgame, because you can see that the hacker or the bad guy can sit with a laptop anywhere in the world, and all they need to do sometimes in order to access a vehicle from remote is as little as just knowing the VIN number of the vehicle, and they can get control into the vehicle. They can get information or private information about the location, about all kind of sensors in the vehicle, microphones, right? There are video cameras inside the vehicle and outside, and so forth. And of course, there are functions that you can take control over if you're able to do it, to exploit it. So imagine doing that from remote. This means that if it's so easy to do it to one vehicle, then you can do it to 1,000 vehicles, or maybe to 1,000,000 vehicles. So this is where the risk and the impact grows exponentially. So this is a real situation that we want to take care of. And of course, the regulators took notice of that. So in recent years, I'm sure most of us, if not all, are aware, in recent years, we have automotive cybersecurity regulation in different countries, in different regions. Probably the most mature one is the UNR 155, which is part of the UNECE organization. So in other words, the European countries and a few other additional member states, Japan, Korea, and some others. But we also have similar regulation coming up in China and in India and in other places in the world. What we see here is an example from the standard, the ISO 21434. It's an international standard, right? It's for automotive cybersecurity. It's like a state-of-the-art document. So on its own, being a standard, it's not a regulation. Having said that, because it is being referenced by many of the regulations that I mentioned, practically speaking, this is becoming part of the regulation. And of course, it's covering a lot of different aspects of automotive cybersecurity, but for the context of our discussion, take a look at this clause 1012 from the ISO 21434 that said that testing should be performed in order to make sure that we are minimizing the amount of unidentified vulnerabilities, right, in the component or in the vehicle. Right? And you see here some examples of what kind of testing, vulnerability scanning. We of course highlighted that for the purpose of this discussion. Some other kind of testing, like fast testing and penetration testing. It's important to note that those statements or clauses of the ISO 21434, they could be either recommendations or requirements. In the case of 1012, we see here the RC that said that this is a recommendation. Having said that, if you look at the next one, 1013, it states that if you choose not to perform all those testings, as prescribed in the previous clause, then you have to provide a rationale. And 1013 is a requirement. It's not a recommendation. It's not nice to have. And since it's going to be pretty hard these days to argue that there is no need to scan for vulnerabilities, then this is becoming much closer to being a requirement than to being just a recommendation. So let's take a look at the good old V model. I think we're probably all familiar with it. It's a model of in manufacturing in general and in our context for automotive software development. Just really in a nutshell, for those of you who are not too familiar, if you look at the left side of the V model, this is where we have the planning, the project planning. So we have requirements analysis. We have all kinds of design phases for the system, for the architecture, for the component. Then if you continue, imagine the V model as a project timeline that flows from left to right. So we started with the planning, and then at the bottom of the V, we have the implementation. This is where we build the product, and in the case of automotive software, this is where we write the code, right? And then we continue to the right side of the V model is where we're doing our testing, and we have different levels: component testing, integration, system testing, and accepted testing. And of course, we see that the V actually continues because now, when we have the start of production, this is not the end of the journey. This is really just the beginning, because the vehicle is going to be on the road for years to come, and we still need to maintain it. So this is the traditional V model, and then came automotive cybersecurity and the requirements and the regulation that we talked about. So typically, what happens is that you have the threat analysis and risk assessment, or TARA for short, and we are doing it, of course, during the design phase, right? So we do that, then we write the code, and then traditionally, again, we saw in the previous slide, we need to do all kinds of testing, including vulnerability testing. Traditionally, this was done towards the end of the development process, while we are doing those system testing, acceptance testing. And there are implications to doing it kind of late in the game. This is where the whole conversation about shifting left kind of enters. So you see here in the next slide, this is coming from applied software measurement kind of concept. It's a very well-known concept. If you think about, again, this project timeline, and what is the timing where you are testing to look for software defects or bugs, or in our context, finding weaknesses and vulnerabilities. And the cost of repairing those defects grows exponentially the more you wait in the project timeline. So if you take the two extremes, right? On the left side, the left that you can get is when you were actually doing the coding, and then comparing to the end of the process where we're about to release the product. This is exponentially more expensive, hundreds of times more expensive to fix the same problem. So in other words, it's much more effective for everyone to discover those problems earlier in the game. So let's take a look at that, but also additional types of challenges that we have when we want to create a vulnerability scanning, vulnerability management kind of process and program. And let's take a look, let's kind of separate between the two main phases, right? On the left, we have the implementation. In other words, this is when we write the code. So the main personas here are the developers. And on the right, we see kind of the acceptance test. This is where we are no longer talking about the code because in many cases, we don't have the actual source code. We got, from our suppliers, we got pieces of software, sometimes in the form of binary, and we still need to do the vulnerability scanning. So starting from the implementation phase on the left, the first challenge is to create the software bill of material, the SBOM, because we are now writing the code, right? We have a lot of pieces of code. It's not very straightforward to get visibility into the accurate SBOM at every phase, which means that there will be a lot of manual process involved in that. Of course, this is not great for us. We want the developers to spend their time developing awesome software, right? We don't want them to spend it on all kind of over type of process. So this is one challenge. Another challenge, as we just discussed, is the cost of detecting those issues late in the game. So this is costly, but it's also an impact to time to market, right? So regardless whether it's the component like an ECU or whether we are looking at the entire vehicle from an OEM standpoint, if we are discovering things late, then we might have an impact on the time to market, the delivery time, which of course has big implications. So looking on the right side, now we have the product kind of almost ready. We're doing acceptance test. Some challenges, starting with the context. So let's say that we discovered a vulnerability, and on its own, the vulnerability could be critical. Still, it's important to understand the context. Where do we have this piece of software? What is the hardware? What is the component? Because if this vulnerability is associated with, let's say, the ADAS system, then obviously this is very, very sensitive and very, very critical. Now, assume the exact same vulnerability in a much less critical component, maybe some ECU that is in charge of the ambient lighting, or maybe the windows. So sure, it has some impact, probably not as high priority as if we had it in the first case in things like games. So the context is important. Going back to SBOM, right? Previously, we talked about the challenge of getting the SBOM from source code. Now we're talking about binaries. Again, this is not always straightforward. Imagine that you're getting binaries from your suppliers. Some of them are AutoStar binaries, some of them are different types of binaries. You don't always have visibility into the SBOM, and you're not always sure that you have the most accurate, most up-to-date SBOM for you to scan for vulnerabilities. And eventually, of course, we have all the formalities that we need when you're doing the auditing, when we have verification that we meet and we comply with regulation. Then, of course, we need to provide all kind of reports. And this is part of the whole process. So that was really a really quick introduction into vulnerability scanning, into the challenges, into a little bit about regulation. We'll go back and talk about regulation later on in the presentation. But at this point, let's move on and start talking about how do we shift left and how do we do vulnerability management during the product development phase, in other words, when we are still writing the code. Jonathan.
So thank you, Noam. So as Noam said, now we'll talk about the two different phases and do a kind of deep dive into how we can manage vulnerabilities, both in the development part and in the testing part. So starting with the development phase, we can see that the benefits are quite clear. By moving our security testing to be earlier in the process, we can discover the vulnerabilities earlier, we can save time, we can reduce the cost of fixing vulnerabilities by quite a lot. And of course, we can accelerate the time to market of our products as we save time by fixing the vulnerabilities faster. So what do we actually get by scanning the source code itself during the development phase? What kind of security insights can we get? First of all, we can look at all the vulnerabilities that can be discovered through the source code. We can see all the licenses that are being used from open source software in our source code, which I'll expand on a little bit later. And finally, we can also see all the guideline violations like CERT-C and MISO-C that were done in the code itself. We'll do a little bit of a deep dive into each one in a minute. So to effectively scan your code for vulnerabilities, there are a few key steps on how to make sure that you do it in the best way possible. So first of all, we have the software development lifecycle integration. Here it's very important that the security testing does not impede the effectiveness of the developers, but is a main part of the workflow and is being done consistently. So by integrating a vulnerability management tool directly into the developer's workflow, into their lifecycle, we can make the testing much more seamless. Once we have that kind of CI/CD pipeline installed with the security testing, we can do the actual security steps. First off, doing the SBOM generation, where we take the source code and we generate the software bill of material, which contains all the third-party and proprietary software libraries used in the source code. Then we can do the security flaw detection, detecting all the vulnerabilities, all the coding standard violations, all the things like the unencrypted keys that may be used or additional comments that may have been put in the code but are not meant to stay there. Finally, once we have detected all the security flaws, we have the job of assessment and response, looking at all the vulnerabilities and prioritizing them accordingly to the risk of the vulnerabilities or of the risks, and making sure that we have good visibility into our next steps, that the developers and the team know what to do next after we've generated all of these vulnerabilities. So let's take a look at an example of how this may be used in real life. So here we have an example GitHub repository, Automotive Universe, which some of you might know. This repository is, as the name might suggest, is very automotive specific. And you can see it in the languages that are being used, C++ and Python and some C. So it's very embedded / automotive focused. And here, by integrating the security tools directly into the repository, we can check each new pull request or each new commit or each new branch for any potential vulnerabilities. So in this example, we can see that a new pull request was submitted to the repository, and immediately after the pull request, the pull request itself was scanned, and vulnerabilities were detected in the new code that was submitted. And here we can create rules that say that if a certain level of high and critical vulnerabilities were found, then the pull request will automatically be rejected, and the developer will have the next steps on making sure that they mitigate those vulnerabilities. And if we'd like, we can also do a deeper dive into the insights that were found and see all the detected vulnerabilities, the detected license risks, and the guideline violations directly in the vulnerability management application. So just to summarize again what I spoke about, we're starting here on the left in the code repository itself, whether it's GitHub, GitLab, or Bitbucket. From the source code, we can generate the SBOM, the software bill of material, from which we can do two things. First of all, we can do the CVE detection, detect all the vulnerabilities that affect the SBOM. In addition to that, we can do the license management. Once we generate the SBOM, we see all the third-party or open source software that is being used in our code. Each open source software or OSS has its own license. Some licenses may pose a legal or operational risk if they are used in commercial products. So it's important to be aware of all the different licenses that are used across the code and be alerted if any of them may pose an operational risk. In addition to the CVEs and the license management, we then have the security flaw detection, which is the things like the CERT-C and MISO-C, the coding guideline violations, or the things like unencrypted keys, emails, or any other comments that may pose risks if they are found in the code. Once all of this information is found, we then have the prioritization engine, which takes all of the information and provides the developer with the best next steps on how to perform, which can then be submitted to the ticketing system like Jira or ServiceNow, so that the project managers can make sure that all the actions are followed upon. So now let's take a look at the right side of the process. We now spoke a little about the implementation phase. Now let's take a look at the supply chain side, where we get our components from our supply chain. So what are the benefits of actually scanning the binaries or components we get from our supply chain, from our tier 1, tier 2, or our open source vendors? So first of all, there is of course, the regulatory compliance, where we must make sure that our final product is secure. But there is also the security risk, where when we use a supply chain, or we have many different vendors in our supply chain, each different vendor may introduce new critical vulnerabilities into our products. This can be a big risk, both operationally to the company, but also to the end user. So once we understand that, we can also understand how to effectively scan the binaries that we get from our supply chain for vulnerabilities, and divides into three main components, quite similarly to the source code phase. First of all, we have the asset management. Here, we can, again, automatically create the SBOM and map it directly to our automotive assets, starting at the vehicle level, all the way down to the hardware level, to the software level, and to the SBOM itself. Once we have done the asset management, we can then correlate our assets to vulnerabilities. We should continuously scan our assets for new vulnerabilities, whether they come from public or private databases. Once we have all the vulnerabilities, the next step is, of course, the assessment and response to those vulnerabilities. Here, one of the main things is that we do correct prioritization for those vulnerabilities, which takes into account the automotive view, that some vulnerabilities may or may not be exploitable with our specific architecture in the vehicle or in the ECU. So this is quite an important step, and we must make sure that we are doing it with the automotive view in mind. So looking back again at the vehicle asset management, it's important that when we do the asset management, it is not flat, so that we can have a clear view on which asset is actually affected by which vulnerabilities. Whether we are an OEM and we're looking at the vehicle view, or whether we are even a tier 2 or 3 supplier who is developing a software or firmware that will then go to an OEM, we must have a clear view into which vulnerabilities affect which components in my supply chain. Then once we do that, the way that we do the vulnerability detection is also important. We must continuously scan for vulnerabilities, not only that affect our SBOM, our software, but also our hardware, which may have less vulnerabilities, but each vulnerability is more critical most of the time than software vulnerabilities. And these vulnerabilities can come from two different sources. First, we have the public vulnerability databases, sources like NVD, JVM, or CNNVD, which publicly post the vulnerabilities that affect commonly used libraries. But then we also have the private vulnerabilities. For example, AutoSAR, which of course is widely used in automotive, does not have any public vulnerabilities in NVD or in any other database. But these vulnerabilities But AutoSAR does have vulnerabilities. They're just not publicly posted. These vulnerabilities come from either penetration testing or they come from the AutoSAR vendors themselves. So it's very important that we have some way of making sure that these vulnerabilities are also scanned when we submit our asset management. So again, looking at the process flow of how to find vulnerabilities in supply chain, start all the way on the left with our supply chain. Whether we get an SPDX, which defines the BOM, the bill of material of our vehicle, down to the software level, or we get a binary file, an image that represents the actual issue. From that, we can do the SBOM extraction, which can happen automatically to extract the information, the full SBOM. We then connect the SBOM to our asset management. And the asset management can either be done in the vulnerability management tool, or it can be done in an external tool and be integrated with the vulnerability management tool. Once we have all of our assets in place and they are connected to the relevant SBOM, we can then do the vulnerability detection. Even as mentioned before, we must make sure that we are not only connected to the public vulnerability databases, but we also scan the private vulnerabilities that may come from penetration testing, from vendors, or from our own proprietary development teams. Once we have all the vulnerability information and we know exactly which assets are affected, we can then do effective prioritization and using both the information about the exploitation of vulnerabilities, things like the known exploited vulnerability database from CISA, but we can also take into account the actual configuration of our assets, what hardware is being used. Can the vulnerability actually be exploited in the way that the library is being used in my vehicle? This is very important to take into account. Once we have all the vulnerabilities prioritized according to our engine, we can then follow up on them depending on the phase of development, whether we can go to the ticketing system or the developers can then mitigate the vulnerabilities, or we can send the information to the XDR and have the relevant playbooks on how to act if the vehicle or ECU is on the road. So with all of that in mind, let's move on now to the next part of seeing how we can integrate all the vulnerability information, which we just spoke about, into the risk models in our TARA. So one important thing to understand is that even though the TARA is done quite early in the V model, quite on the left, this does not mean that we are done with the TARA. The TARA is meant to be used continuously during the entire life cycle of our assets as a kind of key metric to assess risks. And the TARA is constantly updated as the requirements of the components change, or the design of the components change, or if new updates when the vehicle is already on the road are pushed onto the vehicle or onto the ECU. The attack paths change over time, the risks that affect the component change over time, and this is most notable with vulnerabilities. If a new vulnerability is found and it affects a vehicle that is on the road, the TARA must also be updated to guide us in the best way possible on how to address this vulnerability. So now let's dive into our TARA automation tool at AutoDesigner and see how we can integrate the vulnerability information into our TARA. So here we can see the PlaxidityX AutoDesigner, which auto-generated all the risks and attack paths automatically from the vehicle architecture or the ECU architecture. Here we can see a list of all the different attack paths based on how the different components are connected to each other in the ECU. You can see here which threat is connected to the attack path, and we can see also the attack feasibility assessment. This is something that is generated automatically from the PlaxidityX database. And we can see here that each attack path has a different level of severity, which comes from the different information we have about how each component is connected to each other. Now, let's jump into our supply chain security product. But we can see that here we have the QNX, just an example is here, the QNX hypervisor, which has a very large list of detected vulnerabilities. As you may know, Linux and QNX has quite a lot of vulnerabilities. We can see here that in the product we have many different assets that have many different vulnerabilities, and we can filter in this view specifically for our QNX hypervisor, and we can export all the vulnerability information. Once we export the information, we can then directly feed this information into our Auto Designer product. And here we can see that once this information is imported, the vulnerabilities are automatically connected to the relevant attack path by using the CWE of the vulnerabilities and using the stride method for the attack path. We can see here we have an example attack path that has a vulnerability connected to it. And if you remember before, the attack feasibility of this attack path was actually medium, but because we have a critical vulnerability connected to it, or that was directly connected to it because of the information we have about the CWE information, the attack feasibility jumped from medium to high. And this is essentially how the vulnerability information can affect the Tara information. So hopefully you find this useful, this information useful, and we found the connection between the vulnerability information and the Tara interesting and something to look forward to. And now going back to Noam, we'll talk about how we can comply with new regulations that are constantly coming out.
Thank you, Jonathan. So kind of, and this will be the last topic I would like to discuss during this session. Circling back to the discussion about regulation, if you remember the beginning of the session. So automotive cybersecurity regulation, you could say is a moving target. No pun intended. It's moving slowly, but it is evolving. And new requirements are coming up, new regulations are coming up that we need to take care of. And let's take one example, one recent example. And this is a new rule that was enacted by the US Department of Commerce. The objective of this rule, this is just earlier this year, is to safeguard both national security as well as to protect the privacy of American car owners. And specifically, they are naming a couple of countries, China and Russia, in this case, and specific components of the vehicle are now banned if they are coming from those countries. So this does not apply to the entire vehicle, but the rule is focusing on two specific, let's say, sensitive areas of the vehicle. One of them is the connectivity system, right? The vehicle connectivity system. This is where the vehicle is sharing data usually with the OEM cloud. So this is one area. The second sensitive area is the automated driving system, the ADAS. If you have autonomous driving or semi-autonomous driving, of course, if someone can take control over the system and have access to critical functions, steering the vehicle, braking, etc., from remote, this can have meaningful impact. So this new rule is actually saying, look, in those two components, it is not allowed to include assets, whether they are software assets or hardware assets coming from those specific named countries. And you can see here, it says effective date for software. This is virtually around the corner in terms of automotive. Model year 2027 already, you're not allowed to include software-related assets in those areas. And then for hardware, there's a little bit of a grace period. This will start in model year 23. So what does it mean, right? So this is a US rule, but the implications are not just on US manufacturers, of course, because anyone who wants to sell a vehicle in the US, including global OEMs from Europe or Asia or from anywhere else, has to comply with this rule. The same applies, by the way, to suppliers. If you would like to sell, if you're a supplier, would like to sell a component to any OEM that wants to sell vehicles in the US, you would need to comply with this regulation. So if you remember the discussion that Jonathan just had around around asset management and the importance of having effective asset management. This can be very helpful in these type of situations as well, because here we need to scan, in addition to scanning for vulnerabilities, what we discussed so far in this session, now we need to scan for something a little different, the origin of the specific components. And this is where the risk is coming from. So specifically, now there is a new responsibility and you have to report it annually to the regulator that you are complying with it, that you don't have prohibited assets in certain areas of the vehicle. So, like we discussed before, if you have an effective asset management system, this is a screenshot from our supply chain security product. You can see that when you are looking at a specific ECU, we might get this alert that said, hey, vendors that may be associated with those banned countries are part of this ECU. So you can see that you may have a problem here. If you want to look at it from a more proactive way, you can see that you can produce a report that says, show me all the components where I have hardware or software from specifically associated with China or Russia. So maybe the takeaway from here is that build yourself a strong process of asset management, so you'll be able to also leverage that for future requirement that might come by different regulations. So with that, we are nearing kind of the end of our session. Just very briefly, for those of you who are not familiar with us, PlaxidityX, we are all about automotive cybersecurity. We've been around for over a decade, trusted by OEMs and suppliers to protect over 70 million vehicles. We have a portfolio of end-to-end solutions from kind of DevSecOps, and this is kind of what part of it that we discussed today through in-vehicle intrusion detection solutions and protecting entire fleets from an XDR standpoint. So with that, we are reaching the end of the session.